Welcome to Physics Thai, and today we're going to go through the answers of the multiple choice section of the 2023 HSC Physics paper. So let's start with question number 1, which is from Module 5. The gravitational field strength acting on a spacecraft decreases as its altitude increases. And this is due to one of four things: the mass of the Earth, mass of the spacecraft, density of the atmosphere, and the distance of the spacecraft from the Earth's center. Now, the formula for the gravitational field strength, G, is equal to the gravitational constant multiplied by the mass of the object that is being orbited, in this case the Earth, divided by the radius squared. Now, automatically we can see where there's only two variables within the formula that is within our options, and that is the mass of the Earth and the distance of the spacecraft from the Earth's center. As a result, B and C are excluded. The mass of the spacecraft, in fact, is not involved at all. And so we now have only A and D to choose from. Of course, the mass of the Earth remains constant in this scenario, and so our only option is really D. Question number 2. We're dealing here with power transfer from a power station to a house and the involvement of transformers. Now, this ultimately is about Module 6, which is all about transformers. Importantly here is that the understanding is that when we have, and I'm using the top diagram here, is that the power in must equal to the power out in an ideal situation. You will get power out that is less because of energy loss along the way, and the energy loss is along the high voltage power cables, which is determined by I. That is, we have a power loss of equaling the I squared R. And so in other words, this minus that is equal to this. So you want to reduce I, and the only way to reduce I is to increase V. In other words, we step up the voltage in order to get the current down, and then of course step down the voltage at the other end. And so therefore the only possible answer is that we have a step up transformer, a step down transformer, and we are transmitting it via a high current in order to get our low current, so the answer is C. That's question number 3. This is Module 7, all about the wave nature of light. So we have diffraction going on, and of course we will get interference patterns. Importantly is that the position that's right here, this central maxima, is always a position of constructive interference, and so you will get a bright band right there. This automatically means when we look at our answers, we must get a bright band in the middle. So we have that here, we have that here, so B and D are excluded, but you will get a path difference of 1, 2, and 3 for successive bright bands beyond that. So you're going to get constructive interference in multiple spots. So that means our only answer is C. Question number 4, we have cesium-137 that has a half-life of 30 years. We asked what mass of cesium-137 remains after 90 years if the initial mass was 120 grams. Now, you could work out this in the long way by using the mathematical formula, which is this particular formula here. T is natural log of 2 over the half-life, but you don't need to do that. We're told that the half-life is 30 years. We have 90 years transpiring, so we have 3 half-lives transpiring. And so the fraction that's remaining is 1 over 2, but of course this happens 3 times to the power of 3, which is of course 1 over 8. Therefore, if our initial mass was 120 grams, our final, after the 3 half-lives have transpired, is 120 grams over 8, which gives me 15 grams. And so our answer is B. Question number 5. An exoplanet is in an elliptical orbit moving in the direction shown, and the distance between consecutive positions P, Q, R, and S are equal. Between which 2 points is the exoplanet's travel time the greatest? Now, this is about Kepler's second law. We have an elliptical path, but importantly with our Kepler's second law is that the velocity over here is small and the velocity over here is large. That is, it's moving much slower when it is further away from the star than it is moving closer. So that means, considering our distances are exactly the same between P, Q, R, and S, if it's moving slower, then it's going to take a longer time to move the same displacement. Therefore, S and P is our only possible answer. Question number 6. An electron would produce an electromagnetic wave when it is stationary in a stable hydrogen atom, moving at a constant velocity or moving at a constant speed in a circular path. The critical thing here about this is about Maxwell's analysis, that the generation of electromagnetic waves is as a result of electrons accelerating. So automatically we have stationary excluded and moving at a constant velocity excluded. Now importantly here with B, we have a stable hydrogen atom, and that means that's describing specifically the Bohr model of the atom, where electrons exist in orbits but they are not emitting or absorbing any energy as long as they stay in discrete orbits, which means B is excluded in that case. And so therefore the only possible answer is a constant speed in a circular path. Well, a circular path means it's experiencing centripetal acceleration, and so therefore the answer is D. Question number 7. A proton and a neutron travel at the same speed, and we asked which statement correctly explains the difference between their de Broglie wavelengths. Well, importantly, the de Broglie wavelength is equal to Planck's constant divided by the momentum, which you're going to write is mv. And what that basically means, considering that they're moving at the same speed, it's the mass that's determining their de Broglie wavelength. Well, firstly, the mass of my neutron is greater than my mass of my proton. You find this on the formula sheet. And so as a result, automatically we can say that the neutron must have a greater mass. So automatically that mass greater being for the neutron is important, or the proton has a smaller mass, which is this. So automatically we have excluded A and D. But if the mass is greater, then the wavelength is going to be smaller for the heavier particle. And so in this case, it has a shorter wavelength as a result, and therefore our answer is C. Question number 8, projectile motion. So we have a ball that is launched from a platform at a position A with a velocity u, and it lands in the position shown. And the ball could be made to land at a position B by increasing either the velocity u, launch angle, mass of the ball, and height of the platform. Now, what we're wanting to do here is we wanted to land a shorter path. Now, that means we have a couple of options. Option A is we can make the time smaller to do this. Now, in order to make the time smaller, you have a number of options. You can either lower the height, which automatically means you can't increase the height, so D is excluded. Another way we can think about it is we can maybe reduce the initial velocity, the horizontal velocity, make that smaller, right? So in other words, the time it takes to fall down will be exactly the same with this scenario, but a lower horizontal velocity means it lands shorter. Well, we've got velocity u trying to be increasing in A, so the answer is not A. So we either have launch angle or mass. Well, we should know that the gravitational field strength is independent of the mass, so the object will accelerate the same regardless of the mass of the object. So changing the mass is not going to change anything, so as a result C is excluded, but leaves the launch angle. Now some people say, well hold on, can't we launch an angle that it's like this and fall forward? That's true. But if my launch angle is really steep, in effect, I'm reducing the horizontal component of my horizontal velocity, and so it could land, as a result, a shorter path, and so therefore the answer is definitely B. Question number 9. The graph shows the relationship between the radiation intensity and the wavelength for a black body curve at 4,500 Kelvin. What statement describes the expected difference in the graph for a black body at 4,000 Kelvin? Well, first of all, you should know that if we have a lower temperature, two things happen. The overall intensity decreases, and the intensity being the area underneath the graph is that the second graph we draw must have a smaller area. Secondly, the peak wavelength, according to Wind's displacement law, shifts to longer wavelengths. So as a result, I'm going to draw a graph what it might represent as at 4,000 Kelvin. So we have a longer wavelength, and then we have a curve that is going to be having a smaller area than the previous one. So automatically we can see that the intensity at all wavelengths will be less. That is actually true, so we're going to circle it. But let's look at the other responses. The intensity at all wavelengths will be greater. Well, that's in direct opposition to that. The peak intensity will occur at a higher frequency. A higher frequency means a shorter wavelength. That's the wrong way around, so C is excluded. And the peak intensity will occur at a shorter wavelength. Well, that's actually the same thing. A higher frequency is a shorter wavelength, so D is also excluded. Question number 10. We're dealing here with the rotation of a wire within a magnetic field. Now, what we are looking here is what happens to the force and the torque when we change it from figure 1 to figure 2. Now, if we follow the right-hand rule principle to determine the direction of the force here between x and y, then the force is going to be upward. Now, in this case here, the force is still upward. Why? Because we still have a current that is perpendicular to the direction of the magnetic field, and it's the same strength. So as a result, the force remains the same, and so therefore we have C and D as our two possible options so far. A and B can be excluded. But that's not true for the torque. The torque, of course, is maximum when there is an angle between the vector of the force and the moment arm, or the radius of turn. So as a result, we have maximum torque at 1, and in fact no torque whatsoever at 2. So torque 1 is greater than torque 2. That of course means it's this response, and so our answer is D. Question 11. What we have here is from Module 8, and we're looking at radioactive decay. So looking at the graph, we have our atomic number on the x-axis and the mass number, which is the total number of protons and neutrons. So what we're getting basically is we're getting Z minus 2 occurring for x. Our mass number drops by a number of 4. So we've got A being reduced to a value of 4. Well, that can only result by releasing 2 protons and 2 neutrons. And that means what we are getting is a helium nucleus being emitted. Well, that's alpha decay, and so automatically for x, we can see the only options we have so far is A and B. If we now look at y, we're seeing we're having a Z number increasing by 1, but my mass number actually remaining the same. So what that means is I have gained a proton, but I've lost a neutron because the mass number remains the same. And so that can only be explained by the fact that we have beta decay as a result. So that means what we look at our responses here, we're looking for beta decay, and so there's beta decay. So as a result, our answer is A. You actually don't need to even look at the periodic table, because simply by this analysis you can determine the correct answer. Question 12. Here we have a plate separated by a distance of d and has a potential difference of 1000 volts. And so we increase the distance between the plates and we still have 1000 volts, and we're asked, well, what's the change in kinetic energy if a positively charged particle is moved, in this case, a distance of d, basically from the positive plate all the way to the negative plate. And here, the same distance. In order to work this out, we need to understand what is happening with the electric field. Now, the electric field in this diagram here is equal to V over D. Now, I'm going to use the D that is listed over here for the moment. Now, over here, we have a distance increasing, but the electric field is due to the total distance between the two plates. And so therefore the electric field here, if this is electric field 1, electric field 2 is equal to our voltage, which is still the same, but now it's actually the total distance, which is 2d. In other words, the electric field of 1 is equal to twice the electric field 2. Now, let's now look at our calculation of work done. We have a gain in kinetic energy, which is the work done, which is equal to QV, which is equal to QED. Now, that's fine for this one, but you know for our second situation, the distance now is just this short distance here, which is still D, and our E, of course, is now a half of what we had before. And so therefore the work done in the second scenario, or figure 2, is half that of the first scenario. So our answer is B. Question 13. Nucleus X has a greater binding energy than the nucleus Y. What can be deduced about X and Y? Now, reminder, our binding energy is the amount of energy required to break an atom into its constituted parts. In other words, what in essence happens is when you break the parts together, putting energy in, you actually increase the overall mass because the mass of the parts is greater than the initial nucleus. That means if you go reverse, we have a loss in mass. So in other words, what we have is a difference in mass called the mass defect. So therefore the binding energy is equivalent to the mass defect as a result. Now, important though is that stability is not based on binding energy alone. It's based on the binding energy per nucleon. If it was just binding energy alone, then uranium would be the most stable atom of all, and that's clearly not the case. And so as a result, our only argument here is that it's not necessarily more or less stable, but certainly that if X has a greater binding energy, it can only have a greater mass defect than Y. So our answer is C. Question 14. Planet X has a mass of 4 times the Earth and a radius 3 times of Earth. And the escape velocity of the Earth is 11.2 kilometers per second. What's the escape velocity of the new planet? Well, our escape velocity is equal to the square root of 2gm over r. So what I can now do is I can replace my m with the fact that we have our changes taking place. So I'm going to have the square root of 2g. Now our new m is 4m and our new r is 3r. So what I can now do is actually take the 2gmr out. So I've got the square root of 2gm over r multiplied by the square root of 4 over the square root of 3. Now that value here, of course, for the Earth is equal to 11.2 kilometers per second. All I now have to do is multiply this by 2 over root 3, and the answer as a result becomes approximately 12.9 meters per second, and so our answer is C. Question 15. What evidence results from investigating into the photoelectric effect is consistent with the model of light subsequently proposed by Einstein? This is about the photoelectric effect, and so therefore the mathematical formula for the kinetic energy of any emitted photoelectrons is equal to the photon energy that the photoelectron absorbs minus the work function. Of course, I can rewrite this because the frequency, of course, is also equal to the speed of light divided by the wavelength of that photon. Now that allows us now to interpret our question. The first part says photoelectrons were only ejected from a metal if the light was less than the specific wavelength. Well, in this case, we can see that the photoelectron kinetic energy is definitely determined by the wavelength, and the smaller the wavelength, the more likely it has an increase in the kinetic energy, because the work function is constant. So A seems to be right, but let's look at the other responses. Increasing the intensity of light on the metal increased the maximum kinetic energy of the photoelectrons. The critical point here, this is all about the quantum nature of light, and increasing the intensity of light in essence for the same frequency results in more photoelectrons being emitted, all with the same kinetic energy. So B is incorrect. C. If photons have sufficient energy to eject photoelectrons from a metal, the maximum kinetic energy was independent of the type of metal used. Well, if I have a different metal, I have a different work function, and the kinetic energy clearly is related to the work function in the initial scenario, so C is incorrect. And the probability of photoelectrons being emitted from a metal was proportional to the duration of exposure to light. Well, this is an all or nothing event. In other words, the photoelectron will be released regardless of any time factor. In other words, it either has greater amount of energy than the work function, it'll be released, or it never did, and so therefore it won't be released. So therefore the time factor is not important, and so D is incorrect. Question 16, and this is a really good question. What we have here is two rods that are in essence remaining stationary due to the fact that Y is being suspended by some force that is overcoming the gravitational force acting down. Because there is a force of repulsion on Y by X, we can straight away say that the currents are in opposite directions. So I'm just going to write here the current are in opposite directions. In terms of working out what the answer is, first of all we need to say, well, since Y is supported, we know that the force of X on Y is equal to the mass of yg, its weight. It's being supported, and this is consistent, of course, with Newton's first law. Now, what about X? X, of course, is experiencing a force by Y on X, acting downward. But it's also experiencing, of course, the force of gravity pulling it down, which is equal to mx multiplied by g. Of course, combine all those forces, and you get the opposing force of the normal, applying the force of the table back onto X. And critically, this force here and this force here is exactly the same according to Newton's third law. And so what we can now say is that my of g, the weight of g, plus the weight of x is equal in magnitude of the normal as a result. And so when we look at our responses, the magnetic force acting on x is upward. Well, we've excluded that. It's acting downward. The currents through x and y are in the same direction. We've excluded that. They're in opposite directions. The force of the table exerts on x is equal and opposite to the total weight of x and y. Well, that's what we've got here. So C is the answer. D, the force of the table exerts x is equal and opposite to the force of gravity acting on y. Well, we've excluded that already. So the answer is C. Question 17. And what we have here is, in essence, a swinging pendulum. But in essence, it's all about torque. And what we're really asked is, well, in this situation, when there is oscillating between x and z passing through y, which statement best describes the torque acting on the arm as it oscillates? Well, we know that torque is equal to the force multiplied by the radius multiplied by the sine of the angle between the two. Now, if we look at the force acting in this situation, and we're only dealing in this case with the force acting down due to gravity, which is the thing that's responsible for applying a torque on it, we have a force acting down here, a force acting down here, and a force acting down here. That means, if you look carefully, that this scenario right here, the force is parallel to the moment arm, which is this over here, and so as a result there is no torque at y whatsoever. When we look at these two extremes, we can see we do have some component acting in towards y. That means, as a result, there is a net component in towards y. As a result, we actually have a torque, and which is actually the reason why it swings and oscillates. And so its maximum at x and z and 0 at y, which means B is our only answer. It can't be constant in magnitude and direction because it clearly changes. It can't be 0 at the extremes because ultimately we do get it to accelerate from those positions. And it's not constant in magnitude, but the direction changes. Clearly that's not true either. Question number 18. Now 18 looks at the behavior of particles both within a gravitational field and an electric field. I won't read the whole question, but we're asked basically that if there is a change in mass, what will happen to the path in respect to where it lands? And it's important that what we get is the mass is increased by a certain amount, by a same amount. Let's look first at our gravitational situation. We know, as we discussed earlier, that the mass of an object does not affect the acceleration and thus the range of a particle as it moves in a gravitational field, projectile motion, in other words. And so therefore, if we increase the mass, decrease the mass, we're going to get the same range. And so therefore, if it lands at x in the first scenario, it's going to land at x in the second scenario. So automatically, A and B are our only two options so far. But now let's look at the mass change in terms of an electric field. We know that the force that this charge experiences is equal to EQ. But the mass multiplied by the acceleration is equal to EQ. That means its acceleration is actually dependent on the electric field strength, the charge, and the mass. So if we increase the mass in this scenario for the electric field situation, we have a decrease in the acceleration. If we decrease the acceleration, it's going to take longer to fall down a certain displacement, the vertical displacement. That means it's going to have more airtime, and considering it has an initial horizontal velocity, it's going to have a longer range. And so therefore the only possible answer is A. Question 19 is actually all about special relativity, in specific in terms of length contraction. What's happening here? We have two rows of positive charges that are supposedly moving. Of course, we know that electrons are moving, but we'll use the positive charges. Because the charges are moving in opposite directions, from the perspective of charges in the y directions, two important things can be determined. First of all the other charges within y are staying the same distance. It's like you sitting in a train carriage and saying, what is the velocity of the train carriage further down? It's moving with the same velocity as you, and so therefore you're not going to experience any relativistic effects. It's going to be as if it's stationary. So importantly, the separation between the charges for y from the perspective of y will not change. And so that means this part is correct, this part is correct, but not C and D. So automatically we've excluded C and D as our responses. But the charges in X are moving in the opposite direction. They have a velocity, and so as a result, what you're going to experience is relativistic effects. As a result, you're going to get length contraction. So the spaces between the charges will get smaller. And so as a result, the distances between these charges will get smaller, which means this is our only possible answer. They do not get further away because that would suggest length dilation, which is not what takes place. And now the last question for the paper. What we have here is a question dealing with Hubble's law, which measures the rate of expansion of the universe. And so what we have initially with Hubble's law is that Hubble assumed that the expansion was at a constant rate. Now, how do we know that? Well, first of all, if I draw what the slope represents, the slope is equal to, in our case, the velocity divided by the distance. Now that means, since distance over velocity is time, this is 1 over the time. And as a result, if we invert the value here, we can get a determination of the approximate age of the universe. But the point here is that considering this, it means that the distance any galaxies move with the same time frame is going to be exactly the same. But we know that the universe now is expanding at an accelerating rate. So in other words, when we measure distant galaxies, we discover that they are traveling distances in a shorter amount of time, or greater distances in the same amount of time. And so since our distances are the same in a shorter amount of time, that means we expect that for distant galaxies, we're expecting the slope to increase as a result, if that's true. And therefore, as a result, C becomes our only possible answer, with the slope increasing as the distance increases. Well, that's the answers to the 2023 HSC Physics paper for the multiple choice section. Please remember to like, share and subscribe, and please consider supporting me by buying me a coffee. The link is in the description below. My name is Paul from Physics High. Take care and bye for now.